Welcome everybody. This video briefly introduces the buckling phenomenon and the mechanical behavior of bone under compression. If a structure is subjected to a gradually increasing compressive load, sometimes, when the load reaches a critical level, the shape of the structure suddenly changes. This phenomenon is called buckling. When buckling happens, an initial straight member will deform suddenly, producing large displacements. This doesn't always cause yielding or fracture of the material, but buckling is a failure mode which indicates that the structure cannot support the designed load any longer. Basically, the critical compression load can be calculated using this Euler's formula. There are three factors influencing the critical compression load, which include Young's modulus of the material, the length of the bar, and the shape and size of the bar cross-section. In addition to these factors, the supporting conditions of the structure also play a role in resistance to buckling. Let's conduct a simple set of tests on buckling using a ruler. First, put one end of the ruler on the surface of a table, and the other end in the palm of your hand. The two ends of the ruler are free to rotate at their locations. This kind of support condition is called pinned. Now press axially on the top of the ruler and gradually increase the compression force. The straight ruler will suddenly deflect laterally as shown in the figure. Remember your feeling of the force that you applied to the ruler. If you increase force, the deformation becomes larger. This simulates the buckling of a structure with two pinned ends. Now, let's hold the two ends of the ruler tightly to prevent any rotational and lateral movements. The ruler ends are fixed and rotation is not allowed. This is called fixed end condition. Then gradually press axially on the ruler using your fingers until the ruler deforms sideways as shown in the figure. In this case, you will see a different buckling shape from the first one. Also, remember the feel of your hands and compare it with your applied force in the last experiment. You can clearly feel that a larger force is needed in this demonstration than in the previous one. Let's go back to the first experiment, the pinned end condition. But this time, we apply lateral support, which restrains the ruler somewhere in the middle but allows the section to rotate. Press axially on the top end of the ruler and gradually increase the compression force. You can feel that a larger compressive force will be required to make the ruler buckle in this case, compared with the two previous cases. Buckling is a failure mode of soft bone tissues. This type of failure is called buccal fracture, which is also referred to as impact fracture. In this type of failure, one side of a bone bends, raising a buckle, without breaking the other side of the bone. It usually happens when sudden compression is applied to the bone. This type of fracture usually happens in children under 10 years old. That's because their bones are softer and more flexible than adult bones. So the injury makes the bone bend and buckle, rather than break. For example, when a child falls onto an outstretched hand, an impact compressive force is exerted on the wrist, and buccal fracture happens. Another example of buckling in the human body is related to the tibia, which withstands the compression of our upper body and femur, due to gravity, and the support from the ground. In a normal situation, people's tibias are straight. But in some special cases, as shown in the figure, the patients got serious buckling on their tibia, and the load distribution on their knee joint is pathological. The compressive contact stress in the knee is one of the important subjects that researchers care about the most. There are two common approaches to predicting stresses due to contact. One approach is to conduct mechanical experiments using equipment and apparatus. In a study, Tambaya and his colleagues tested the contact stresses in the knee joint, in deep flexion using 5 cadaveric specimens. This figure shows the equipment that they used for the experiments. They applied loading conditions for various phases of walking and squatting on the cadaveric knees, using a quasi-static mechanical machine. A thin film pressure sensor was inserted into the cadaver tibiofemoral joint space to measure the force distribution and contact area between the femur and the tibia. The peak of the contact stresses was recorded for the conditions which simulate the heel strike, the single limb stance, the toe-off position, the deep flexion at 90 degrees position, and the flexion greater than 120 degrees. The study found that the contact stresses were significantly larger in deep flexion at 90 degrees, reaching the damage limits of cartilage. Computational simulation is another popular way to analyze the bone response to any kind of load, including compression. In a study, Donahue and her colleagues established a computational model of the human knee joint to investigate the contact stress between the tibia and femur due to compressive force. The study used a single right knee from a cadaveric specimen, a male subject of age 30. A computed tomography system was used to capture the geometry of the cortical and cancellous bone tissue with a dimension of 0.5 millimeters. To capture the shape of articular cartilages, menisci, and ligaments crossing the knee joint, a non-contacting laser-based system with the dimension of 8 microns was used. After constructing the knee geometry, the model was imported into an advanced mechanical computational software, named Abaqus, and the stress and the contact area between the femur and tibia were measured for the compressive load of 800 newtons, while the joint was positioned at 0 degrees of flexion. This study showed that the transverse ligament, the anterior cruciate ligament, and the medial collateral ligament only slightly affect the contact stress between the femur and tibia during walking. Furthermore, considering rigid or deformable models for the femoral and tibial bone tissues does not affect the contact stress between the bones.